Good morning, everyone. First of all, I am very thankful and grateful for Azrieli Fellows program for giving me the opportunity to express my work in front of you all. The topic of my presentation is polyoxometalates connecting molecular and solid state chemistry. Here, I will be discussing about what are the molecular and solid state chemistries, how they are differ from each other, and what is the need to connect them together, and how polyoxometalates, it is difficult to pronounce, so we will just call it POMs. How POMs can play a significant role in connecting both of these chemistries. So, I will start with a simple example what comes under the category of molecular chemistry. Here we can see it's a paracetamol tablet. But as a chemist perspective, we can see that it is a discrete molecule that is a water soluble, and if we talk about its applications, it used as a drug, and in many chemical reactions, it used as a reactant. Now let's move to the solid state chemistry. I will give an example which is every girl's favorite, that is the diamond. If we see it as a if we look into its chemical structure, it is actually an extended form of carbon networks that held together and form this solid diamond. It is the hardest natural material that is water insoluble, and its applications are in jewelry, in electronic devices, in semiconductor devices, etc. So here we got a brief idea that in molecular chemistry, we deals with the small molecule that are water soluble, whereas in solid state chemistry, we deals with the solid molecules. Now let's understand it more deeply. Let's start with the molecular chemistry. It deals with the entities on the molecular level. Let's take an example. Suppose this is a water molecule. We can see water from the eyes, but we can't see a single molecule. Suppose we want to break this hydrogen oxygen bond. So how much energy will be needed? It will be studied in the molecular chemistry. Let's go to the solid state chemistry. It investigates materials on larger scale. Suppose rusting of iron that we can see from our eyes, it will be studied under the solid state chemistry. Also, the molecular chemistry is mostly the solution state study, and the solid state chemistry is mostly solid state study. If we talk in terms of applications, molecular chemistry applied in areas such as drug discovery, material synthesis, catalysis, and environmental science, whereas solid state chemistry used in fields including material science, semiconductor technology, energy storage, and nanotechnology. Now we understand that both these chemistries have its own advantages and certain limitations. So is it possible so we can merge both these chemistries and can make an interface? So we can use the advantages of both the chemistry. It is a challenging frontier area in chemical science, and here where Professor Ira Weinstock's research group works on the interface of both the chemistries. So let's start the importance of working on the interface by a simple example. Here it is a solid gold, and here it's a molecular gold. In between these, there is an interface where gold can show different properties and applications. So it is an example of the interface between solid metal and the molecular metal. It is a very well known and well studied since long time. But what is rare is the interface between the earth abundant metal oxides and the molecular metals. It is very rare, particularly in the solution. And it is very rare to achieve. So we achieved it by using the polyoxometalates. Here is an example. So you can see here on the right hand side, it is a solid titanium oxide that is a very well known material used in the food industry, also in the semiconductor devices. And on the right hand side, it's a molecular titanium oxide clusters. So in between, we have trapped the small-scale titanium oxides by using the polyoxometalates. And what we formed is soluble structures at the interface between molecular clusters and solid titanium oxides. So now we'll understand why these POMs are that much beautiful materials that we can use to trap the solids in very small form. What are polyoxometalates? That is POMs. POMs are molecular metal oxide anions based on transition metals and oxygen. In the periodic table, you can see these are the all elements present on the earth, and the highlighted ones are those which can form polyoxometalates. So what I have shown here is that the gray one, this is the basic construction unit of forming a polyoxometalate. The gray one is the metal and the red ones are the oxygen. We can also present it as a polyhedra. So it is a basic construction unit. When this oxometalate join together, it forms polyoxometalates. So we'll see further that these oxometalates can combine together in different fashions and can form different structures. So why POMs are capturing chemist interest? What is fascinating about these materials? So first thing is POMs demonstrate a huge diversity. It shows versatility in shape and size. And being the part of Azrieli Foundation, we know the beauty, significance, and importance of the diversity. So these POM material also shows the diversity. Here is the diversity of the POMs. You can see here that the polyhedra that I have shown earlier, the basic construction unit, it can join in different fashions and can form various type of structures. And we can synthesize the material according to our need, and we can choose any of these POMs. Another best thing about the POMs is POMs exhibit various remarkable properties. Like, first one is the elemental composition. It means we can incorporate many elements in the POMs. Second one is it is stable in oxygen and water. They are non-toxic and their synthesis is inexpensive. Their production is scalable, and they also show the electronic properties because they are electron rich in nature. Now I will show another example, synthesis of a POM-complexed hematite core. Hematite, also known as the iron oxide. So here we can see that this hematite, it present in the bulk size, but it is a traditional water oxidation catalyst. And water oxidation is an important reaction in the green fuel generation. But when we dissolved in water, it is susceptible to degradation when we dissolved in water. So when we use the POM to trap it into the solution form, we form the POM-complexed iron oxide. So we trapped it into the 2 to 3 nanometer size, and it was also the highly active water oxidation catalyst, and it was water soluble and stable. So we were able to harness the properties of solid materials and taking it into the realm of molecular chemistry to understand it deeply and completely and to get the mechanistic pathways in detail. So now to summarize it, it bridges the conceptual divide between molecular metal complexes and solid state metals, allowing the use of a versatile toolbox of solution state methods typically reserved for molecular catalysis. So now I will thank you all with this note. Thank you for being here. Thank you.